Okay.
here and I saw them.
Okay, so here's the next big thing. And we briefly talked about that in the forces unit way back in the simple days of physics 1.
Long ago.
An acceleration test. Oh, how simple.
Just like do that one again.
And now you go back and you look at that test and go, wow, I gotta miss anything on that one. All right, so electric fields. This is going to be chapter 20. And we're kind of starting to get into the conceptual part of physics, okay? In the sense that you can see the results of it, but it isn't like, hey, let's, look at friction. Oh, I push that and it slows down. You know why that happens? It's friction, okay? Electric fields take on some weird manifestations, but there's a whole bunch of different ways that electric fields are similar to gravitational fields. Gavin?
Is any of this even real?
Okay, stupid question.
Yo,
is physics?
Like, is this theory or is this proven stuff?
Mr. Burkhamp, what were you?
That we're about to learn about.
Guys, remember when you did the balloon in the static and it moved? Was that real?
Nathan?
Compared to other tests, is this like a middle, hard, easy?
Like the other one.
Guys, how about we just start this unit, bro?
I know.
Okay.
I think you and Dad are done. Sorry.
Okay. So, if you look at kind of the history of physics, initially you had two fundamental forces. You had gravity, and this is really important in terms of that equation. So gravitational is big G, M1, M2 over D squared. Okay? We've dealt with this.
Yeah.
You have a fundamental unit of the universe mass, okay? M1, M2 over D squared. You have this universal gravitational constant, 6.67 times 10 to the negative 11.
Nice. There it is. Ready to learn.
Big guy, what do
We
you
walked in.
Newton meter squared over kilogram squared. Yes?
What is that symbol under, like it's next to 4 pi?
I'll explain.
That's right. Just
Look like
Give it
that.
It's epsilon naught.
Does it look like what? Is this like a
It's
bad
epsilon naught.
or is there some big green things?
Okay. I don't feel well when I'm about this close, so can you stop talking and just giving you the assignment? Okay? If you want to go gossip and schmuck around, go outside. You have the universal gravitational constant, 6.67 times 10 to the negative 11. You have 2 units here of mass, you get kilograms squared. Inversely proportional to d squared. Okay? What you've got. The beauty of this is that number one, you don't have to worry about it being repulsive. It's only attractive, and it's dependent upon the only thing you need to know to calculate that force are the 2 masses and how far apart they are. Newton never actually came up with the value of G. He just said, hey, it's some constant of proportionality. Henry Cavendish went out, had the large spheres, and he actually came up with the value. From there, we were able to weigh the Earth. So this was the first one mathematically that they were able to quantify. Cavendish came up with the value of big G. Now, they knew that there was something happening with the electrostatic value. So if you look at this, and on your equation sheet, there's 2 different versions of this force. One is 1 over 4 pi epsilon naught. So this epsilon naught, and it's an odd dot. If you come over here on the back side of this yellow sheet, you have 2 values. You have a vacuum permittivity value, and then you have a vacuum permeability value. One is epsilon naught, one is mu naught. Okay? We'll deal with them later in terms of the speed of light. So there's 2 ways that you can calculate the electric force between 2 charged objects, depending on how much of a purist that you want to be. So if you take 1 over 4 pi and this value of epsilon naught, okay, which is 8.85 times 10 to the negative 12, and it has some jacked up units of Coulomb squared over Newton's meter squared, okay? And if you come in here and you actually do the math, so somebody take your calculator, take 1 over 4 pi, 4 times pi, times 8.85 times 10 to the negative 12, and let me know what you get.
8.99 times 10 to the 9.
Okay, so we'll just call it 9.0 times 10 to the 9. Okay, so out of Maxwell, James Clerk Maxwell, famous Scottish physicist, he's the one that came up with Maxwell's equations that are named after him. If you ever get a chance to study those, they're horrible. They're very enlightening, but they're incredibly tough to work through. So the pure form of this is 1 over 4 pi epsilon naught. Okay, so that's the pure weight. That's what Maxwell came up with. Functionally, what we use is just K, okay, which is just a constant. So the constant, which is just much easier to use, and this is what's also on your sheet, because you over here it has Coulomb's constant, 1 over 4 pi epsilon naught, which is 9.0 times 10 to the 9 newtons meters squared over Coulomb squared. So this is what we always use. If you're a pure hardcore, hey, I'm a fan of James Clerk Maxwell, use 1 over 4 pi epsilon naught, but it's functionally 9.0 times 10 to the 9. So here's where this variation happens. So the charge, the force between two charged particles, you have 9.0 times 10 to the 9th. What?
Is there a name for this equation?
It's just like you have, it's just the force between two charged particles. It's just electrostatic force. Though it doesn't have like a fancy name. Okay. And you got Newton's meters squared over Coulomb squared. Now, the reason that they put the charges in absolute values over distance squared is that you have different combinations of charges. So mass is a one-trick pony. Mass is just mass. All you got. You don't have to worry about it being negative. So in terms of charges, you have different options. You could have a positive charge and a negative charge. You could have a negative and a positive. You could have a negative and a negative, and you can have a positive and a positive. So there's actually 4 possible combinations of charges that you can have. But mathematically, if you have a positive and a negative, no matter what, is that going to be an attractive or repulsive force? So anytime you have opposite charges, that's going to be attractive. And anytime you have the same charges, that's going to be repulsive. So this is another way that this is different from gravity. Gravity, you don't have to worry about waking up in the morning and go, hey, I'm going to check the gravity out. Oh, man, it's a repulsive gravity day. That's going to suck. I was going to go bowling. Okay? Throw the ball. Goes towards the ceiling. Okay? Huh?
Surely they'd have like upside down bowling.
Oh, there you go. It's upside down bowling. Yeah, there you go. And the pins are on the ceiling. Or you also don't have to worry about it like being a weak gravity day. It's like, oh, it's a weak gravitational field day. Oh, maybe I can actually dunk today.
I gotta put on my
It's a
bed
gravity
shoes.
day. Or maybe I can hit that drive 300 yards, whatever. So yes.
Okay, so you have r squared, but then when you rewrote it, you wrote it as b squared.
It's the same thing. R squared or d squared. It's just the
It's the
distance.
same thing.
Yeah, it's either a radius or a distance. Just like if it was,
Oh, distance, not diameter?
yeah, no, not diameter, distance. Not diameter, not diameter, not diameter. So like if you had a proton and you had an electron moving around it, you would talk about a radius. If you're talking about 2 protons that are just sitting there, then you'd be talking about a distance. Okay? Just like if you had a satellite orbiting around the Earth, you would be talking about a radius. If you're talking about the two bowling balls, you'd be talking about a distance. Okay, so it's just a radius or distance, doesn't make any difference. Okay. So if you look at the units, so this Q is charge. So there's one specific number that you'll know just from using it a lot. So down here it has elementary charge, okay? And that has a value of 1.60 times 10 to the negative 19 coulombs. So this is the charge on one of two things. This is why it's called the elementary charge. That is either the amount of negative charge on a chihuahua, or an electron, or it's the amount of positive charge that's on a proton or a St. Bernard. So this is somewhat counterintuitive. And here's the reason why. So J.J. Thomson discovered the first subatomic particle. He found the electron. That cathode ray tube shot him through. Then we'll talk about electric fields later. But Thomson shot this stream of particles, which you didn't know what they were, through a cathode ray tube. The cathode ray tube is just basically like a glass tube, and you hook it up to a very strong battery, and it creates these particles that move through. And what he did is that he put like a battery, like he put a positive plate on one side and a negative plate on the other. And so what he found is that the particles, instead of going straight through, were bent up towards the positive plate and away from the negative plate.
We talked about this in physics 1.
So, huh?
Talked about this in physics 1.
So this basically acts somewhat as like a Lemming problem, where you have these particles coming through and they're deflected. Because they're deflected, you know there has to be a force acting on them because of Newton's first law of motion that says, hey, these particles go straight until an outside force acts upon them. And so because they went up towards the positively charged plate, that's how we figured out that they had a negative charge. Thomson actually never found the mass. He found the charge to mass ratio. Okay? It's a subtle thing, but it's important. But the main thing out of Thomson, he found these negatively charged particles. And we'll go through the math once we get into magnetic fields, how they actually determine the mass of these particles. Basically, you make a move in a circle, and if you know the radius of the circle and you know the force that's acting on them, you can figure out the mass of the particles. Okay? Because if I want to find the mass of an electron, okay, and that's another number that you're going to need here, okay, so it's got like proton mass and neutron mass. Notice those are basically the same number, 1.67 times 10 to the negative 27. But notice the electron mass, that electron mass is 9.11 times 10 to the negative 31st. So that's the mass of an electron. But the mass of a proton or neutron is 1.67 times 10 to the negative 27 kilograms. Now, both of those are extremely small numbers,
Right.
okay? And they are. And that's like the difficulty in finding these values. It is like, hey, what's the mass of an electron? I don't know. I'll take the magic pair of electron tweezers and grab one out of the air, and I'll put it on a scale and go, oh, here's the mass, okay?
So the proton neutron weighs about 1,000 times more than the electron.
That's about 1,800. If you do the math, it's about 1,800.
Okay.
So there's this, and they're both small, but if you do the math, that's like an order of magnitude of about 1,800. Okay, it's like 10 to the 10. So what that means is if you had a scale and you put one proton on one side, it would take about 1,800 electrons on the other side to balance that out. So this is why I said, hey, you look at the structure of matter, you have the St. Bernards and the St. Bernards and the sheepdogs. Those are the big chunky things in the middle, very, very large. They just hang out. And then around them, you have the chihuahuas running around.
Like Teacup Chihuahua.
Huh?
Like Teacup Chihuahua.
Like the really tiny chihuahuas.
Okay, whatever, chihuahuas, whatever kind of chihuahuas you want.
Pequeño.
So the electrons are like the chihuahuas. They're the annoying thing. So you have this cloud of chihuahuas, and inside you have the Saint Bernards and the sheepdogs.
Is that accurate?
Oh, horribly not accurate, but that's what ChatGPT generated. That was my one venture into using
Oh my god, that is
Chat.
Chat. Yo, I thought that was like an actual.
Yeah, the Saint. Here's how you remember: the Saint Bernards have a T in them,
From over there.
and they're positively charged. Sheepdogs are just chilled out. They're just like whatever. Okay. So, quick refresher on how this all played out. So Thomson figured out that there were electrons. So by default, what else did there have to be in the universe? Why?
Because it's opposite of negative.
Yeah, because if the universe only created, let's say the universe was having a bad day. The universe says, screw it, I'm feeling negative. I'm only going to make negatively charged particles.
Blow to smithereens.
No.
Everything would have been
Nothing
like
ever happened. Everything
We
would
wouldn't
repel each
be
other.
here. Why?
Everything.
Everything would just repel each other, right?
Yeah.
Okay? And the same thing could happen if the universe opened up and it was reading its horoscope and said, oh, you're going to have a positive day today. And the universe said, I'm going to make protons.
You don't have to. You're just a bird. You don't have to answer it. They only answer to you.
So you answered it. If he doesn't answer it, use the elder.
He's the alpha.
Use the elder of the spirit. That's why.
Better go say something else.
He's about to hang up on that.
Just imagine. Can you imagine if the Eagle faculties are like a tribe? Elderberg. We had a predicament. The light is away.
I think you need to delete Instagram.
More annoyed in just a second.
Oh,
You'll see. Okay,
I'll see what.
so the universe says, hey, we're only going to have positive charges. Won't work either, because then everything would repel as well. Maybe the universe says, hey, I'm just going to have a neutral day today. I'm just going to make mass and I'm not going to have any charge on it. Great.
She's gonna stay there.
Nothing, we wouldn't exist either. Okay? So the universe conveniently made all three of those. And the reason that we have to have neutrons is because if we didn't have neutrons, we wouldn't have a stable nucleus. We couldn't even make helium without neutrons. Okay? So conveniently the universe said, I'm going to hit the trifecta. I'm going to make protons, electrons, and neutrons. Why? We don't know, it did, and we're thankful for it. Now, where it gets weird is that, and this was predicted before we actually found it. It's like, what's the square root of 4?
2. Plus minus 2.
Or
Plus minus.
plus or minus 2. So, out of the primordial energy of the Big Bang, it cooled down. As the universe cooled down, you began to make mass. And that came from the shortened version of Einstein's equation, E equals mc squared. C is the speed of light. This is, oh yeah. And E is the amount of energy. So what that means is that this door can swing both ways. If you have mass, that can convert into energy. And this is what happens on the sun. Right now, every second that goes by, hundreds of thousands of pounds of hydrogen is being converted into helium. And we'll talk more about this later. The 4 hydrogen atoms, if you compare that to the mass of the 1 helium atom, and this is a whole step-by-step process. This is the condensed version. Here's what you need to know for now. The 4 hydrogen atoms have slightly more mass than that 1 single helium atom does. And the difference between those 2 masses is what gets plugged into this equation, and that tells you how much energy is produced. Okay? And it works because if you look at the units, that's kilograms, and then you have the speed of light, which is meters per second squared. Adam, go. That's for you.
Am I in trouble?
Did they find
Go.
the stash?
Uh-oh.
The stash.
Just
Oh, they
open the
used
door.
Open the
Okay.
door. Just Adam needs to go out.
Happy birthday to you. Happy birthday to you. Happy birthday, dear Adam. Happy birthday to you.
Why did you like not do the second? You said I recording.
This was
Well,
the
that's
last thing that.
Wait, really?
I thought it would be like.
Mr. Bird, can Mr. Bird, can I do that on my birthday?
Thank you.
Mr. Bird, Mr. Bird, can I do that on my birthday? Okay, I'm gonna do it regardless.
I did, but then I took pity on you. You didn't even bring enough cake for everybody.
Come on, man.
Had I known that, I would have said
We
one.
can cut it into
That's like barely-
17th.
Cut it into 17.
No, it's okay. Everybody can get a try.
We're going to talk to Pronto.
Hey, okay, I would want you to talk to us at 1 o'clock.
Hold on. Just chill out.
And it was like somebody's like getting called out. I don't know. Not a.
Bye, Adam.
Bye. Have a good day. Did you guys bring like a fork for him or?
No.
Okay.
Use your hands.
Back to physics.
Happy birthday, Adam. How old are you now?
Oh, gambling time, gambling time.
That's what you love, right? You go buy a lottery ticket today, Adam?
Physics.
Bro, visit.
Now, everybody says, oh, Einstein and Equation was a genius for coming up to this. Well, look, if you carve it back, how do you calculate kinetic energy?
1/2
1/2 squared, right?
What the freak? Oh my god.
Notice that that's kilograms times meters per second squared, right?
I don't think you actually
Which gets you joules. Now, could have Einstein said, hey, maybe just E equals MC? Everybody would have laughed at him. Why? What do you get when you multiply mass by velocity? Momentum. Okay? Everybody would look at this and go, dude, you get momentum. You're taking mass times velocity. You get momentum. So in terms of the units, it had to be c squared. That's the only way you get units of joule. The beauty of what he figured out was that there was nothing in front of it. There was no fractional 1/2, 1/3 pi, anything like that. That was the beauty of what he did. So here's the point. Universe comes into being. Big Bang, pure energy. You go through a whole bunch of different stages. Hyperinflation, things like that. We have what's called the cosmic microwave background radiation. That's kind of proof that the universe happened, because no matter where you measure this cosmic background radiation, it's like the remnants of this event. But what should have happened is that the universe should have produced equal amounts of matter, what we're used to, and antimatter. So antimatter acts just like matter, but it has the opposite charge. So matter, what we consider matter, the electron has a negative charge. Okay? Antimatter, you have what's called a positron,
What the freak?
which has the exact same mass as the electron, but it has a charge of a positive 1.60 times 10 to the negative 19th coulombs. An electron has a charge of negative 1.60 times 10 to the negative 19th coulombs. Now,
Isn't it just a positive electron?
so yeah, it's just like then you have negatively charged protons
Yeah.
instead of positively charged protons. So here's the deal. So the very short version of this story is that it's just like when you take the square root of 4, you get plus or minus 2. So the universe should have created equal amounts of matter and antimatter. But here's the problem with that. Anytime like a positron, antimatter, runs into normal matter, what we're used to seeing in the universe, they annihilate each other and it goes back to pure energy. Okay? So if the universe had created exactly equal amounts of matter and antimatter,
Bang, bang.
we wouldn't be here having this discussion because the universe would just continuously be returning back to energy. Big Mike.
So on the little number sheet, for elementary charge, that's what it says, the 1.6 something.
That's either an electron or a proton.
Okay, so it's really plus or minus. Wait,
Yeah.
plus or minus.
That's why it's called the elementary charge,
Okay.
because it's the same thing on a proton or an electron. So one of the great mysteries, yes, Alyssa.
Wait, so is antimatter a real thing? Or
Oh,
is it
absolutely.
Isn't it like
We
almost
produce
impossible
it.
to
Why?
decide?
Wait, really?
Oh, yeah.
It's
Yeah,
like-
but here's the problem. No, yeah, and it's cool. This is one of the debates was, does antimatter interact with the gravitational field the same way that matter does? And it was only maybe like a year ago they collected enough antimatter to actually measure that, and antimatter works the same way in the gravitational field as matter does.
Isn't it the most expensive thing in the world?
Well, here's the problem.
Isn't it? It's hard.
Is that, oh, no, antimatter is not everywhere. No.
That'd be
If
bad.
antimatter were everywhere, it's like bam, 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 okay? No, no. Neutrinos, which we'll talk about later.
What?
small.
Yes.
So that sounds like
Okay,
pretty
wait,
low.
so what exactly is antimatter? How does one produce?
Okay.
What does it do?
Okay.
Bad question.
So, no, this is a very valid question.
I wanna know.
So it goes back to Einstein's equation of E equals mc squared. Okay? Goes back to that idea. So if you look at E equals mc squared, the problem isn't understanding that you can take mass and you can convert that into energy. Okay, that is not the problem. Conceptually, that is not the problem. The conceptual problem realizes that if you have enough energy, okay, like electrical potential energy, something like that,
Could you turn it back?
if you have enough of it, you can make mass appear out of energy. Okay? The door swings both ways, right? So if I have enough energy, and it's a lot,
How much?
you get into what's something called high electron volts. We deal with electron volt later. Okay? Big number. So if you have enough energy, you can make that. So the problem is we can make antimatter, in particle accelerators. We can make antimatter. The problem is keeping it. Because you can't keep antimatter like, oh, I'll just get some and pour it in my cup. Okay? What would be the problem? Boom! Because as soon as it interacted with anything, matter-wise, it's just going to annihilate
It would have
itself.
to be
So you have to keep it trapped in a magnetic field.
in a vacuum.
In a vacuum, in a magnetic field.
Oh, that's hard.
Yeah.
That's
So
hard.
that's
That's
why
hard.
it's tough to get large quantities of it. Because you have to
What-
produce it.
You know what the largest quantity produced is?
No, I don't know. But it's tiny. Big Mike.
So let me be clear.
Right.
But you have,
Let me be clear.
you got normal matter,
Wait, so
Which
this
is what we're made of.
then you got antimatter,
Yeah.
but then you got dark matter, but that's just normal matter, right?
Oh, we don't know what dark matter is.
Oh, we don't know that?
Oh, dark matter's the thing. We didn't know what it is.
Okay, so
Isn't that
then-
what
It's
it's
real,
Well,
right?
and dark matter and dark energy make up, depending on which source you look at, roughly between 70 to 80%.
Is it real though?
Yeah, like we're missing, it's embarrassing. We are missing huge chunks of our universe. We don't know what it is.
Mr. Bergkamp,
What?
if we don't know what dark matter is, how do we know
We
that
know
it's
it's
making
there,
up
we
that
just don't know.
amount of
Okay,
We just don't know.
here's how they discovered it. Okay? So, what they started to do is they started to look at galaxies. Okay? So here's the best analogy, like the Milky Way is what's known as like a pinwheel galaxy. Okay, and you have thousands and hundreds of thousands of stars circling around an object. Okay? So this is going around like this. So what they started to do, and this is why you had to have very, 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 very good telescopes. That because we didn't even know other galaxies existed until like the 1920s. So we've had two defining moments as a species when we've had our ego burst. One was when we figured out we were just like all the other planets. Okay? It's like, hey, you're special. The note that mom writes to you every day for 18 years, and then the next day you open up your lunch pail and go, you're like all the other kids. You're just average. Heartbreaking.
No, we are
So, but we still held on to the idea that, well, we're at least the only galaxy. Okay, that was cool. We're the only galaxy. And we saw these pinpoints of light in the night sky, but we thought they were stars. Well, then once you began to get good enough telescopes, you realized those aren't stars, those are actual galaxies. And those galaxies have hundreds of thousands and millions of stars in them. So instead of us being the only galaxy, we thought we were cool. We thought we were the cool kid on the block. Oh, we're the only galaxy. Maybe not we're the only planet, but at least we're the only galaxy. Now it's just like, oh, we're just like other hundreds and millions of galaxies. We're just like everybody else. As a matter of fact, we're an average galaxy. There's not even anything special about us. What?
What if it's like that with universes?
That's a whole other thing. We'll talk about later. What?
Could we weaponize antimatter?
No, we are so far off topic.
You guys listen, I read it on
Oh, that's like
1
what
gram
we
would take out
could.
all New York. 1
You
gram.
could.
One
Yo!
gram.
Yes.
Yo!
You could. But the problem
It'd
is
be really expensive.
making it and keeping it contained.
Wait, is that why it's expensive? Because it's.
Yes.
Okay.
Mr. Berg.
So here's what happened.
What if we made antimatter?
Here's how we figured out that dark matter existed. Once we started looking at these galaxies, what we noticed was that these stars were going way, 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 way too fast for gravity to be the only source holding them in. It would be analogous to this, that I'm going to take Hank, and I'm going to take a thin piece of sewing thread, and I'm going to tie that to Hank. And I'm going to take, just using that thin thread or that thin piece of sewing material, I'm going to swing Hank around over my head at a very high velocity. And y'all going, won't happen, right? You're not going to do it. So what would you conclude?
That's not something.
That there's something else
There's no prosperity.
acting on Hank. Because the thread isn't doing it. But you can't see it. Okay? You can't see it. But something else has to be happening to keep Hank moving in a circle. That was the whole observational idea for dark matter. Now we've actually mapped it, because dark matter does interact with light. So we know if there's a region of dark matter, light will get bent. It's actually called gravitational lensing. So it's the same idea. So if we know where a star is in its location, but here's the deal. If that light goes around a lens, this is why it's called gravitational lensing. So if we're here on Earth and we see that light coming in and it gets bent, we think the star is here. Because our eyes trace it back to that origin. In reality, it's over here. So that light is getting bent around this dark matter. So that was the second piece of evidence that dark matter existed, because we saw gravitational lensing of light.
What if that's a
Alyssa.
So is it like a black hole that just doesn't?
Oh, no, black holes are a completely different thing.
Hey, what's the index of refraction for
No.
Wait, so we're saying that dark matter it can be either real matter or fake matter.
Oh, no. We know dark matter is there. We know it's there. The problem is, it's called a WIMP, a weakly interactive massive particle. Okay? So it's kind of a cool thing, a WIMP.
A wimp?
Weakly interactive massive particle.
You don't have to leave.
I will never ask you that on the test. That's just kind of what they call it. We think it's a WIMP, a weakly interactive massive particle.
Can it be an extra critic?
No.
So dark matter
Okay.
doesn't matter.
So
Doesn't matter.
black holes are a completely different beast that has no. It's related to dark matter, but it's completely different. Not the same thing.
Do we learn about that in this class?
Huh?
Do we learn about that in this class?
We will once we get into theoretical physics.
Oh dear.